So today I'll be discussing part C of Graham's Law. So I have here the original process. The original lab environment for studying Graham's Law typically involves a controlled setting where gases can be safely handled and measured. This includes a well-ventilated chemistry laboratory, safety equipment such as gloves, goggles, and lab coats, a fume hood for toxic gases that's involved. The equipment used to demonstrate Graham's Law is most likely a gas infusion, gas collection tubes, a stopwatch, gas samples. And experimental procedures is to prepare different gases with the known molar masses, fill the infusion and apparatus with first gas. Here I have the original difficulties. The original difficulties are understanding the initial hurdles, the safety issues, equipment issues, and information. So for some initial hurdles, we have grasping the inverse square root relationship between rate and molar masses. Safety issues, we have handling gas safety in a laboratory setting is crucial. Some gases may be toxic, flammable, or reactive. And equipment issues, most of the time, the equipment issues are accurate measurements of gas values and collaboration of equipment to maintain accuracy. So for the original motivation, we have Mr. Thomas Graham, as usual, a Scottish chemist in the 19th century, aimed to study for diffusion and effusion. He discovered the Graham's Law.
And this is my part of the slideshow. Starting with the original process. In early experiments, Thomas Graham worked in a basic lab using glass tubes, vacuum pumps, and small plates with tiny holes. He studied how quickly different gases escaped or mixed by measuring how long it took for them to pass through these openings. By comparing gases under the same conditions, he noticed that lighter gases move faster than heavier ones, from which he formulated Graham's Law. Original difficulties. Thomas Graham faced many issues early on because his lab was basic. He struggled to keep his pressure and temperature the same, and his tools were not very precise. He had to do all his calculations by hand. He didn't have a calculator, which led to mistakes, and working with gases also meant he had to be extra careful to avoid accidents. Original motivation. Thomas Graham's original motivation was driven by scientific theory and his desire to provide evidence for emerging kinetic theory of gases. Graham proved that gas diffusion depends on molecular mass and velocity. His work helped people understand that gases are made of particles that are moving and lighter molecules are faster than heavier ones. Original benefits. Graham's discovery quickly made it easier for chemists and physicists to calculate gas properties with greater accuracy. These advancements offered a scientific basis for understanding the behavior of gases and mixtures. His research also made it easier to collect, sample, and measure gases in experiments. Modern process. Scientists use tools like vacuum chambers, mass flow controllers, pressure sensors, and computers to precisely measure how gases move. Many industries use gas permeable membranes to separate gases such as oxygen, nitrogen, and hydrogen. In these controlled systems, gases are introduced and their movement through those membranes is automatically monitored. Lighter gases pass through these membranes faster than the heavier ones in accordance to Graham's Law. Different methods. Modern experiments rely on advanced tools. These tools are measurements much more accurate and efficient than they were in the original Graham's era. Labs are kept clean. Data on pressure, gas flow rate, and temperature are collected automatically and are handled by software, which helps show how molecules act and find ways to use this knowledge. Modern benefits. Scientists use advanced sensors and software to automatically collect and process data on pressure, gas flow, and temperature. This helps them analyze how gases move, calculate diffusion rates, and model molecular behavior. Understanding gases in such detail has a lot of benefits across areas such as medicine, energy, and environmental science. Future expectations. In the future, research based on Graham's Law is expected to make gas separation and purification more efficient and eco-friendly. Improvements in automation, sensors, and software may help scientists study gases at similar scales and under extreme conditions. This could lead to new applications: medicine, clean energy, environmental process, and industry. Inspire technology that we have not even imagined. Thank you.
Okay, my name is Mackenzie Hill, and I will be going over my slides for part C of Graham's Law. Okay, so we have original process. So in the early 1800s, labs were small, simple rooms with open flames, glass tubes, and metal tools. Glass flasks and metal stands for heating and mixing chemicals, hydrogen glass generators, and platinum sponges used for satanic lick test. Wolfgang created a lamp, which is this lamp, where the hydrogen glass passed over platinum, showing chemical reactive and gas activity. Okay, then we have original difficulties. So Wolfgang struggled to find accurate measurements of elements, masses, and to compare properties without proper tools. He also struggled with early lab glasses often would crack or leak under heat and glass pressure. Wolfgang would have to manually record data, making small calculations impossible. Not impossible, very possible. Original motivation. Okay. Wolfgang wanted to find patterns among chemical elements to better organize chemistry. His goal was to share that element properties were related to their atomic weights. His discovery of law of Trinidad was intentional. Now we're moving on to original benefits. Wolfgang found relationships between element properties. Law of Trinidad help organize elements and predict new ones. So then we have the periodic table. Okay. Now we're going to move on to modern process. So modern chemistry labs, highly controlled, ventilated, and digital. Diffusion cells and vacuum chambers measure gas flow under precise conditions. Scientists test gas diffusion rates using advanced sensors and data logging, applying Graham's law to steady motion of air and fuel. So then we have a picture of this. Then we're going to move on to modern differences. Okay. Scientists today use digital sensors and computer and precise gas measuring tools instead of glass tubes and flames. Modern labs use seal systems, fume hoods, and protective gear to prevent exposure to gases. Gas diffusion and reactive rates are tracked with high-speed cameras and real-time data systems. Modern chemists use computer models and simulations to predict how gases behave under any conditions. So now we have a digital sensor. Okay, then we're going to move on to modern benefits. Wolfgang discovered element of patterns help form the periodic table, which helped all modern chemistry. Environmental science is used in air quality monitoring and making sure pollution is controlled. Gas diffusion system measure gases concentrate in the industry. Then we're going to move on to future expectations. using Graham's law principle and developing faster and safer gases separation for environmental systems, space exploration, more efficient gas management, and spaceships using diffusion and